All right. So let's revisit the last example that we were doing with capacitors, dielectrics. Let's do something. Okay. So here we go. So I have a capacitor which I will charge to a potential difference of 1.5 volts just by increasing the battery voltage. I will have a capacitor plate spacing of 10 millimeters or 0.01 meters, which is that. And then I'm going to charge the capacitor. So the cap is charged, and then the battery will be removed. What you want to remember anytime you have a capacitor that is charged and the battery is then removed is that Q is constant. Charge cannot flow onto or off of the capacitor because there's no path for it to go to do so. And then battery removed, and then the dielectric will be inserted. And we'll see what happens. So let me charge my capacitor up. And we'll use glass. Has a dielectric constant kappa of 4.7. And then I disconnect the battery. And let's look at all the meters here. Got my voltmeter. And I got my meters here that are going to read capacitance, plate charge, and stored energy. So I insert the capacitor. Remember, the whole idea behind dielectrics is that you have insulators whose charges get polarized, but they don't flow. That's why it has to be an insulator. They get polarized, creating an induced electric field within that opposes the external electric field generated by the plates, reducing the overall electric field, reducing the voltage, increasing the capacitance. Okay. And so whenever I slide the dielectric in, the capacitance increased. Let's just talk about each individual thing though. Charge, the electric field, the potential difference, the stored energy, and the capacitance. So the charge, same. All right, there's no path for the charge to leave. The electric field got reduced. Oh, I don't have the electric field. If you look at the electric, there's only 4 of them there. There's about 20 of them there. So the electric field gets reduced by what amount? By an amount equal to kappa, right? You want your E new, it equals the E original divided by kappa, divided by the dielectric constant. So it goes down by a factor of the dielectric constant. And it's not capital K. It's a Greek letter. It's a weird Greek letter that looks more like that.
Okay.
It's literally kappa, like the Greek letter kappa.
Okay.
Now that we can see just by analyzing, thinking about the electric fields that get induced. The electric potential, though, because it's directly proportional to the electric field by this equation, then if the electric field goes down by a factor of kappa, then the electric potential does as well. So the electric field goes down by a factor of kappa. And if we watch the voltage, right, we start at 1.5 volts, we end up with 0.319 volts. I bet when you divide 1.5 by 4.7, you get 0.319. The potential energy, that's the stored energy. Stored energy obviously goes down, right? Why does it go down? Well, remember, electrical potential energy is just, electric potential. The general equation for electric potential is electric potential energy per unit of charge. The amount of charge hasn't changed, but the electric potential went down. Potential difference went down, which means the electric potential energy had to go down by the same amount because they're directly proportional. And it should make sense. I have weaker electric field. I have electric fields that are opposing the external electric field from the plates. And so I'm reducing the amount of potential energy. These guys are attracted to the charges. The positive charges up here have an attraction to the negative charges down here. That is now less than. It's like being in a weaker gravitational field. There's going to be less potential energy. Okay. So the stored energy goes down also by a factor of kappa. But then our equation for capacitance is charge divided by potential difference. Measured coulombs per volt, i.e. farads. So if my potential has gone down, I should be able to load more charge on it if I have a source for it. They're inversely proportional. So now by inserting the dielectric and reducing the electric field and reducing the potential difference between the plates, I have now increased the amount of charge that I can store on that capacitor. And so C increases by a factor of kappa. And just to show that, I'm going to connect the battery. I'm going to end up with more charge. Right? I end up with more charge. I connect the battery. Oh, now I have a larger capacitance because I have a smaller potential difference, so I can load more charge on there. Make sense? Cool. Move on. I hope they can see. I hope y'all can see the writing on the board in the.
Let's go back to
vector addition. Let's go back to the beginning.
Yeah.
Let's start at the beginning.
That one Neil deGrasse Tyson documentary.
That one what?
Neil deGrasse Tyson documentary. Like, I don't know. It just goes back in time and talks about like the universe progression.
Cosmos?
Yeah.
Yeah.
Let's start back.
You know that's a remake, right?
From the original.
The original by one of the coolest humans ever lived, Carl Sagan. Yeah. Who actually discovered Neil deGrasse Tyson when he was still in high school and invited him to go to the university that he taught at. Yeah, so it's kind of like passing the torch. Yeah. Very sad. Carl Sagan died way too young of brain cancer. Very sad. You watch his last interview. It's a very insightful interview on YouTube. Anyway, okay, so now we're going to have the same setup. Let me reduce this guy back down. 0 volts. Can I get it to 0? Oh my gosh, let me just reset it. All right, so now we're going to have the same potential difference, 1.5 volts. We're going to have the same, we're going to start, okay, for some reason I have 5 millimeters on this one. That might be come into play. So let me change the plate separation to 5 millimeters. Capacitor is charged. Battery remains connected. When the battery remains connected, notice in the last one when I reconnected the battery, charge changed. The amount of charge the amount of charge on the capacitor changed. And that's because when the battery remains connected, it's the potential difference across the capacitor that is constant. So if the potential difference is constant, then you can get charge loaded on and off. Again, because you have a pathway for that to happen now. So the battery remains connected. I don't want to do that one. I'm sorry. We're going to keep it at 10 millimeters. I don't know what I was thinking there. I blame Gianni. What happens when you sit in the front? You're the scapegoat. All right, so plate spacing 10 millimeters. The capacitor is charged. The battery will remain connected. And I will insert a dielectric. And let's talk about what's going to happen to the same things. Let's talk first about what happens with the potential difference. Then we'll talk about what happens to the capacitance. We'll talk about what happens to the electric field. We'll talk about what happens to the total charge. All that stuff. All that fun stuff.
Will they do the energy or no?
Energy. That's what I said. Gosh, get off my back. Okay. So let's charge it. Let's put my voltmeter. And remember, when you got your voltmeter, I got one here, or a multimeter. We'll be learning how to use these when we study circuits. You can put it anywhere on this wire. The potential difference between this part of a wire and that part of a wire, especially since no charge is flowing, is literally zero. So we can put it anywhere that's connected to the capacitor plates in question. Okay, just to kind of, just to keep the wires out of the way. Let's do it like this. Okay. And we will keep the battery connected, so delta V is going to be constant. Right? The positive plate of the capacitor is going to be at the same potential as the positive terminal of the battery, regardless of what I do with the dielectric. And so I take the dielectric and I slide it in, and the capacitance increased. I have to change the scale. That's what I'm doing up there. The capacitance, the plate charge, and the stored energy all increase. Right? So why is that? Well, the potential difference stayed the same. Right? Before we get to actually the capacitance, the energy and stuff, let's look at the electric field. What happens to the electric field? It stayed constant.
Because V and D are constant.
V and D are constant. Right? I didn't change V, I didn't change D. So the equation, electric potential difference, equals electric field times the distance, plate spacing. Delta V didn't change, D didn't change, so electric field can't change. Right? Notice that, and think about it, the electric field didn't change, but I got more charge on the plates. Remember, when we slide the dielectric in, you get an induced electric field that opposes the actual electric field. So in order for this to be true, charge must flow onto the capacitor plates. Mm-hmm. So the electric field, same thing. We watch the capacitance increase. So we know the capacitance increase. Let's look at the equation for capacitance. Capacitance equals charge over potential difference. So here, the potential difference again didn't change. But in order for the electric field to remain the same, we needed more charge to go on. We can logic our way through that. We needed more charge to maintain the same electric field, according to the electric field voltage equation. So more charge, we get more capacitance. By a factor kappa. Yep. So increased by a factor of kappa. And just so you know, that's the equation on the formula sheet. One of the equations on the formula sheet for capacitance is kappa epsilon naught area over plate separation. That's what's on the formula sheet. We started with C equals epsilon naught A over D. But then once we start dealing with dielectrics, we put the factor kappa in there. I don't know what y'all are laughing at. Shh. You're going to get written up. Okay. Charge we already saw increased by a factor of kappa. And I'm going to leave some of this as an exercise on the question assignment so you guys can figure it out based on these original principles here. So what about the stored energy?
Up B kappa for the charge.
What's that?
Up B kappa for the charge on the board.
More B kappa.
You guys are so mean. Okay, so potential energy, and I want to point this out again, because this was the explanation, or this was the problem that one of you, I'm not going to, I think it was Ox, had with one of the questions on the quest assignment, the last one. Because the potential energy stored in capacitor is 1/2 Q times potential difference, right? But the reason that you couldn't have used that one in that particular problem is because when you change the potential on a capacitor, you have to put more or less charge on it, unless you're changing the actual physical geometry. So we can also use the equation. We can take C equals charge per unit volt, and we can say, all right, well, Q is C times delta V. So we can say it's also 1/2 capacitance times delta V squared. This is on your formula sheet. Exactly like that. And then we can also say, well, delta V is charge divided by capacitance. And so I can substitute that in for delta V here. So I get that the potential energy is Q squared over 2C. For some reason, that's not on the formula sheet. Not really sure why. But this one actually I see more often than the other ones. Or at least the use of it. See more often than the other ones. Because I'm not saying here, I'm just saying those are the three equations for the stored energy in a capacitor. If I wanted to talk about how the energy is going to change here, knowing all this information, I'd probably want to look at this guy, right? Because this guy is only going to have one thing here changing. Delta V is going to be constant. Delta V is constant. So if delta V is constant, and I know the capacitance will increase, then the stored energy will have to increase. Okay? By kappa. By a factor of kappa. B kappa. Increase B kappa. All right, so that's my spiel. I want to give you the rest of the period to work on the quest assignment and tomorrow. It's not terribly long. There are some tricky questions. You're going to deal with a spherical capacitor with an inner and outer plate. It's going to look more complicated than it actually is. If you understand the basics, you can just apply them to a spherical capacitor. The only difference is that the electric field is going to change within the spherical capacitor, whereas it doesn't in a parallel plate capacitor. Okay. And then you'll also have this. Let me point this out too, so you don't get too confused. You'll also have a question towards the end that has a parallel plate capacitor, which creates an electric field inside of it. And then you're not going to have one, but two different dielectrics inside, like this. Where this guy will have kappa 1, this guy will have kappa 2. Dielectric constant. The thing is you get the same effects, right? You get negative, positive with an induced electric field here. And then the same thing down here. So it's the same way. To deal with that, you just want to deal with the potential difference across this guy plus the potential difference across that guy equals the potential difference across the whole thing.
Yeah, and that sort of goes with what I was talking about. So kind of just like a sheet,
like inside?
Yeah, if you had like a bit of a dielectric that doesn't fill the entire thing, then you do like the sections for air and then...
Exactly. If you had a capacitor, and I was going to put one of those on there, but the only good one I found was like 6 parts.
Oh.
And I told you guys it wasn't going to be a long quest assignment, so I didn't want to...
Make that the whole quest assignment.
Yeah.
No, but there's other things that you need to know about.
No. Okay.
So if you have like a dielectric like in here,
Yeah, exactly.
yeah, like that, then yeah, you would deal with the potential difference here and then there, and then you just deal with it like that. But the same general principle will apply. You'll still have, the induced electric field in here, and then the external field that just passes right on through it. All right.
I guess that also brings some interesting equations of like the specific electric field in regions inside that of differing
And you can, I've seen questions like that where you can determine the electric field here, right? And you can use Gauss's law for that. You can draw your Gaussian cylinder like this. You can draw it like that, right? Yeah. Good stuff. Good stuff. Absolutely not. Yeah, it was
Yeah, like I normally go before class.
in SD Hall.
Yeah, but there's
Were they cleaning it or something?
I think so.
I feel like